Network architectures. Now, considering the different types of neural network architectures, we have three different types. The first one, it is single layer feed forward network architecture, multi-layer feed forward neural network architecture, and recurrent architecture. The architecture of the neural network is linked with the learning algorithm used to train it. In a single layer feed forward, we have a single layer. In multi-layer feed forward, we have more than one number of layers. In the recurrent layer neural architecture, we will be iteratively performing the operation. Coming to the single layer feed forward network architecture or the neural network architecture, we can see we have the input layer of source nodes, and finally with that we have output layer of neurons. So whatever we are seeing here, these nodes that are highlighted in green color, so this is a layer we have. So hence this is considered as a single layer feed forward neural network architecture. So we have the input or the source nodes, we have the output layer. So we have the nodes here where each of them they are considered as a neuron. So if I consider a single neuron, it is similar to a single perceptron performing the operation. So this type of network architecture, they are called as single layer feed forward network or neural network architecture. Moving to the next one, we have multi-layer feed forward architecture, where we have the input layer, then followed by we have two layers here, okay, where whenever we have more than one layers, then those type of neural networks, they are called as multi-layer feed forward architecture. So we have one layer here and one more layer here. So and we have what this layer, whatever we have, it is called as hidden layer. And with that, this network is considered as 342 network, because the source node we have 3 here, whereas here in the hidden layer we have 4 nodes, and in the output layer we have 2 nodes. So this type of network, it is called as 3:4:2 network. Finally we have the output layer. So we have the hidden layer, we have the output layer, we have the input layer, and this type of neural network architecture, they are considered as multi-layer feed-forward architecture. Now, suppose if any architecture is having more than or greater than one hidden layer, then those type of neural networks, they are called as deep neural network. Fine. So what we can see here, we have the input layer. The input to these input layers may be from the previous layers. So it is how the input layer is considered. So this input layer will be will be once again sending the information to the hidden layers. So hence they are considered as feed forward. We are always feeding in a forward manner. Hence these type of networks, they are called as feed forward. We have single layer, we have multi-layer feed forward network, where in a multi-layer feed forward network we have three different types of layers. One is input layer, the hidden layer, and the output layer. And this network can be represented as 3:4:2 network, because in input layer we have 3 source node, in the hidden layer we have 4 nodes or the 4 neurons, and in the output layer, how many nodes or neurons we have? We have 2 neurons. Coming to the feed forward networks advantage, they their lack of cycles are present in feed-forward networks, because the computation proceeds uniformly from input units to the output units. Then activation from the previous time step plays no part in the computation, as it is not fed back to an earlier unit. Simply computes a function of input values that depends on the weight settings. It has no internal state other than the weights themselves. Fixed structure and fixed activation function G. Thus, the function representable by a feed-forward networks are restricted to have a certain parameterized structure. So these are some of the advantage of feed-forward networks. Coming to the neural network learning, the objective of the neural network learning given a set of examples, find parameter settings that minimize the error. So this is what the objective of the neural network learning. So given a set of examples, the training example, find the parameter setting. Parameter setting includes either learning the weights of the neural network, or considering the value of the learning rate when we are learning the perceptron or the neural network. So the parameter settings is one thing that we are into the neural network learning, setting these parameters in such a way that they are minimizing the error. The aim is to obtain a neural network that generalizes well, that is, that behaves correctly on new instances of the learning task. Okay, with the neural network learning, we have some programmer specifics. So what are programmer specifiers? So number of units in each layer. So this is what a programmer has to specify. Connectivity between the units. Then unknowns are the connection weights. So this is what we are supposed to learn. So that is how the neural network, okay, these are the programmer specific, these are unknown things. So we'll be using all these things to perform a neural network learning. Therefore, ANN is specified by an architecture. Architecture tells a set of neurons and the links connecting the neurons. Each link has a weight. So that is the architecture. A neuron model, the information processing unit of the neural network. This is nothing but the learning rule that we have to adopt. A learning algorithm used for training the neural network by modifying the weights in order to solve the particular learning task correctly on the set of training example. So these are the three things that has to be specified to an artificial neural network: an architecture, a neuron model, the information processing unit of the neural network, a learning algorithm used for training the neural network by modifying the weights in order to solve the particular learning task correctly on the set of training examples. With this, learning in neural networks, that is the learning task, it can be supervised or unsupervised. With supervised data, so as you already know, we have labeled examples, that is input, comma, desired output. In unsupervised, we have unlabeled examples, that is different realizations of the input. Task performed by using supervised learning is classification, pattern recognition, and regression, task clustering, and content addressable memory. NN models can be used as perceptron, Adeline, feed-forward neural network, radial basis function, and support vector functions to perform the supervised learning. Here, self-organizing maps and upfield networks, they can be used to perform the unsupervised learning. That is by using neural network models. Coming to the multi-layer networks, these multi-layer networks can also be considered as multi-layer perceptrons. So perceptrons are rather weak as computing models since they can only learn linearly separable functions. Yesterday I told how to differentiate between the linearly separable data as well as the not linearly separable. So the perceptron are rather weak as computing models since they can only learn linearly separable functions. And when I was talking about the activation functions, some of the functions are linear functions and some are non-linear function. Thus, we focus on multi-layer feed-forward networks for non-linear sigmoid units. Thus, we focus on what? Multi-layer feed-forward networks for non-linear sigmoid units. It is nothing but the activation functions we are using here is non-linear in nature, not the linear function. Multi-layer network to represent highly non-linear decision surface that are much more expressive than the linear decision surfaces of the single units. The non-linear activation function used, it is called as a sigmoid activation function, which is given as g of x equals to 1 divided by 1 plus e to the power of minus x. So this activation function, it is called as sigmoid activation function. So, which is non-linear. So, for multi-layer perceptron or for multi-layer networks, we need a threshold unit, that is a differentiable or a differential threshold unit is what that is required for the multi-layer networks or the multi-layer perceptron. Multi-layer feed-forward networks, if you consider Multi-layer feed-forward networks extend perceptron, that is one layer network into how many layers? N layer, by partitioning units into layers 0 to L such that the lowermost layer number, layer 0, indicates what? The input units. The topmost layer numbered L contains the output units. Layers numbered 1 to L are the hidden layers. It is nothing but we have input units, then the hidden layers, and finally the outputs. So these are inputs are connected to the hidden layers, and once again from here to here these are connected. Finally the outputs are connected. So here we are number from 0 to L. So this 0, it represents the input units. 1 to L, okay, represents what? The hidden layers. And finally the last one represents what? That is the output units. Connectivity means bottom-up connections only with no cycles, hence the name feed-forward nets. Input layers transmit input values to the hidden layers, hence do not perform any computation. Whatever the computations are performed, the computations are performed at the hidden layer as well as the output layer. Layer number indicates the distance of node from the input nodes. So this is how a multi-feed forward network is considered. So we have inputs x0, x1, x2, x3, and x4, which is the input layer, the input units. Hidden layer we have v1, v2, and v3. Output units we have O1 and O2. Okay, so whenever we have all the units connected to all other units considering each of the layer, so this type of connection, it is called as fully connected network, because you can see here the inputs, all the inputs are connected to all the nodes of the hidden layer. All the hidden layer nodes are connected to all the nodes of the output units or the output layer. So this type of network, it is called as fully connected, a multi-layer feed forward neural network. Hidden units are nodes that are situated between the input nodes and the output nodes. Given too many hidden units, a neural network will simply memorize the input patterns. So given too few hidden units, the network may not be able to represent all the necessary representation. It is nothing but it won't be able to identify all the features or all the patterns with the input we are going to consider. Coming to multi-layer networks and the backpropagation algorithm, as I already told, the multi-layer network represents highly a non-linear decision surfaces that are much more expressive than the linear decision surface of single units, that is a single perceptron. They learn by an algorithm by the name that is called as backpropagation algorithm, as they are capable of expressing a rich variety of non-linear decision surfaces. Right? So whatever the single perceptron we talked about, so it is used to perform its operation well on the linearly separable data. Here we are much into non-linear functions or non-linear data. So it is expressing a rich variety of non-linear decision surfaces. What type of unit is used for constructing multi-layer network or multi-layer perceptron? Fine. The type of unit we are going to consider is differential threshold unit. It is nothing but, so already you know, so this is how a single perceptron look like. With whatever we have considered till now a single perceptron, here the threshold unit that we used, okay, for the threshold unit, the activation function we used was linear activation function, like the stepwise step function, or what, a signum function or a sine function. Here the unit or the threshold unit that we are going to consider is differential threshold unit or non-linear threshold unit. So we'll be using what, a sigmoid unit or a sigmoid activation function, a unit very much like a perceptron but based on smoothened differentiable threshold function, which can be differentiated. The threshold output is a continuous function of its input. Here, okay, sigma, the activation is a non-linear function, activation function. The rest all things remain similar to that of what, that of a single perceptron. But here in the multi-layer network, we'll be using what? A differential threshold unit, that is a non-linear activation function. Sigmoid is one such non-linear activation function, which is given by, so sigma of x or z or whatever it is 1 divided by 1 plus e to the power of minus x, which is what? Which is a differentiable threshold function which can be differentiated. The purpose of the activation function is to introduce non-linearity into the output of a neuron, because real world data is non-linear and we want neurons to learn the non-linear representation. Different types of activation functions or differentiable threshold units that can be used are sigmoid, tanh, ReLU, leaky ReLU, and etc. Coming to the first type, that is sigmoid activation function, it takes a real value input and squashes it to the range between what? 0 and 1. Whatever the threshold unit we use in multi-layer networks, they are called as the squashing functions. So also called as squashing functions. So the sigmoid is given by sigma of y equals to 1 divided by 1 plus e to the power of minus y. So this is how the graph is represented, and it is always better never to use this except for what? Except for the output layer. Tanh it takes a real valued input and squashes it to the range -1 to +1. The formula or the function that is used is sigma of y equals to tan h of y, where this is represented as 2 into sigma of 2x minus of what? Minus of 1. Moving to the next one, we have ReLU activation function that stands for rectified linear unit. It takes a real valued input and thresholds it at 0, replaces negative value with what? That is 0. So what it is going to do is, when you just give this sum, or when this sum is processed through this activation function, that is rectified linear unit, we are going to consider maximum of 0 comma y. Suppose if y value is a negative number, it will always replaces that with what? The 0. That is replaces negative value with what? That is 0. This type of functions, they are called as ReLU or rectified linear unit activation function. Now whenever you consider the multi-layer perceptron or multi-layer neural network, this neural network, they always works by using an algorithm that is called as backpropagation algorithm. So as you already know that learning a perceptron is nothing but learning the weights or identifying the weights of the neural network. So here we'll be doing the same operation, but using an algorithm that is called as backpropagation algorithm. Algorithm learns the weights for a multi-layer network, given network with a fixed set of units and interconnections. So learns the weights for a multi-layer network given a network with fixed set of units and interconnection. It employs, okay, the backpropagation algorithm employs what? Gradient descent to attempt to minimize the squared error between the network output values and the target values of these outputs. So here the backpropagation algorithm, whatever we are using, it uses a gradient descent, but it is not going to use a standard gradient descent algorithm, but it is using a stochastic gradient descent to attempt to minimize the square error between the network output values and the target output values of these outputs. So learning the problem faced by backpropagation is to search a large hypothesis space defined by all possible weights values for all the units in the network. So we have a backpropagation algorithm. Now, before we consider a backpropagation algorithm, so using this algorithm, how actually we are going to learn the weights is, first we'll perform the forward pass. Forward pass, it is nothing but doing the calculation similar to the single perceptron. Then after doing the forward pass, we'll calculate error or the loss by using the loss function or the cost function. Then we'll perform what? The backward pass. So hence it is called as what? Backpropagation algorithm. So we'll do the forward pass, then we'll calculate the error. If there is a error, that is a maximum error that is obtained with the target values and the obtained output or the desired output, then once again we'll perform what? The backward pass, and we'll try to calculate or try to update the weights, and again perform what? The forward pass, again calculate the error or the loss. If we have a maximum error, again perform the backward pass. Hence this algorithm, it is called as a backpropagation algorithm. So the backpropagation algorithm consists of the training example, the learning rate. NIN, it represents the number of neurons at the input layer, at the output layer, and the hidden layer. So each training example is a pair of the form what? That is x vector comma t. T represents what? The target value of each of this, or for each of this training example, where x is nothing but the vector of network input values, t vector of target network output values, and nu is the learning rate, n is the number of network inputs, n hidden is the number of units in the hidden layer, and n out is the number of what? The output units. So as I've already told, we are not going to perform any operation at the input layers. Fine. The computation is done at the hidden layer nodes as well as the output layer nodes. In the input layer, we are not performing any computation. So number of network inputs. So it tells how many number of inputs we are considering for the neural network. The input from unit I into unit J is denoted as xji, and the weight from unit I to unit J is denoted as wji. Suppose if we have two input nodes at the input layer and three nodes or the three neurons at the hidden layer and one at the output layer. Now whenever there is a link between the nodes from the input to hidden or from hidden to the output layer, so it is associated with the weights. So how the weights are represented? If this is the first node of the input layer, second, this is the first at the hidden layer, second, and the third, this is the node at the output layer, then the weight is represented as W of what here? It is J and I. The weight from unit I to unit J, it is represented as 1, 1. If I consider here, the weight is represented as J, then I, so it is weight 2 and 1. Suppose if I consider from here to here, it is weight of, it is 3, then 2, J, then I. So this is how the representation is done for the multi-layer perceptron or the multi-layer neural network. Now, coming to the backpropagation algorithm, the first step we are supposed to do is create a feed-forward network with Ni inputs and then N hidden units and N output units. Initialize all the network weights to the small random number, which is similar to the perceptron training rule. Now, until the termination condition is met, what we are supposed to do for each training example associated with the target values or the target output in the training example to propagate the input forward through the network. It is nothing but we are performing the forward pass first. Okay, so input the instance, that is X vector, to the network and compute the output, that is OU, of every unit U in the network. It is nothing but, suppose if I have one input and two hidden layers, then one more output. Okay, so this is the hidden layer, this is the output layer, so weight is associated. Suppose if I just give one input X, so we have one weight here, even the weight is associated, so what we are supposed to do is input the instance X to the network. So input it, what is the calculation we'll do X into W1 or X into W. Fine. Then after doing X into W, so then we'll be sending that to which one now? The activation function. So when you do that, the output is obtained from this hidden layer. So that is what we are supposed to do. Again, we are going to consider the output that is obtained at this layer, multiply that with this weight, and that is the output that is obtained from which one now? That is your output layer. So output OU of every unit U in the network. Then propagate the errors backward through the network. Next, what we are supposed to do? So once after, okay, calculating the forward pass, that is the output for the output unit, we need to identify or we need to calculate the error. So propagate the errors backward through the network. So how we'll propagate the errors backward to the network? for each network output unit K, okay, calculate its error term, that is delta K. So this is the error that we are going to calculate at the output layer. Okay, that is for the each output units. Okay, we are taking that as what? K. Calculate the error term. So the error term is calculated what? By using the formula delta K, which is equal to, that is output unit. Okay, O of K of 1 minus O of K into T of the output unit K minus O of the output unit K. So this is the target value. This is the obtained output from the network. Now in the similar way, the error is also calculated at which layer now? At the hidden layer, that is H. Calculate the error term, that is delta H, at the hidden layer by using this formula. Now when we are calculating the error term at the hidden layer, we'll be always also using what? The output nodes or the neurons at the output layer, and calculate what? The error term at the hidden layers. So delta of H equals to O of H into 1 minus O of H into summation of K belongs to outputs. It is nothing but all the units or the neurons belonging to the outputs. So what we'll do? W, that is weight of what? K into H. Whatever the weights that are present between these two, that is we are going to consider it into delta K. So did delta K is already calculated from where now? From the previous step. So this is the error that is calculated at the output layer. For calculating the error at the hidden layer, we take the help of what? The error that is obtained or calculated at the outer layer. Then after calculating this, what we'll do? We'll update the weights for the weights of the neural network, that is the new weights. The new weights are updated by what? W of Ji, because it is between two then. So we have the weights here, it is always represented from I to J. So Wji of what? Wji, the old weight, plus of delta of Wji, where this delta of Wji is given as what? New into delta J. This delta J is calculated here. At the output layer, it is calculated by using this formula. At the hidden layer, it is calculated by using this formula. So when we are updating the rules at the hidden layer weights, so we need to use here the nodes or the neurons at the hidden layer. So learning rate into delta J into X of J into I. This is the actual input. So this is the step that we need to use it. Now, because we are considering the networks with multiple outputs units rather than the single unit, redefining the error function or the loss function to sum the errors over all of the network output units, we take, okay, the error with respect to the weight vector equals to 1 divided by 2 sigma of D belongs to D. Once again, sigma of K belongs to output because it is a multi-layer network of T of K into D, the target value present at this path, minus of the output that is obtained for this path by using what? The multi-layer network, all to the power of square, where output is what? The set of output units in the network. This one, T, K of D is the target values, and then the output values associated for what now? Associated for the kth output unit and the training example T. So this is the backpropagation algorithm we'll be using, where first we'll do the forward pass, then calculate the error or the loss, then perform the backward pass. So when we perform the backward pass, we go on updating what? New weights for the neural network. So this is the procedure that is followed. So we'll take an example.